Hi, everybody. Hopefully you can see the presentation now.
Looks great. Thanks, Soizic.
Good, thanks. So thank you for the introduction, Phil. I think it was great to see all the things you can do with particle tracking modeling. I just want to highlight before, so there is no disappointment, that I'm going to have a very simple demonstration. So yes, so this is like the base to do the cool thing that Phil can just showed you. There are many particle tracking models currently fully available, and a lot of them are now quite offering a user-friendly approach. Today I chose Parcels because it has this user-friendly approach, and it's also very flexible if you want to model all the very complicated behavior that Phil showed us. But first, a bit of context. So Parcels was developed at a time where ocean models produce very large data sets. And the developers had in mind when they were developing the code that in a few years we may face a situation where many Lagrangian frameworks cannot be used on the latest data anymore. So they developed Parcels with scalability and performance in mind to be efficient and fast for the next generation of ocean circulation models. The user interface of Parcel is written in with Python, and the computational intensive integration are done with C. So it was written so you can have computer architecture experts that can optimize the underlying method without changing the high-level description of the model, which makes the user-friendly approach of Parcel. And something else I wanted to highlight also is that it's developed so you can use NEMO, the NEMO Ocean model, as forcing. And as you know, these forcing are very easily available through the Copernicus service. So this is one of the nice animation that they show on the web page of Parcel. They actually provide the code if you want to do it yourself. So here is some links. So on the website, they offer some very good tutorial documentation. So they make it very easy for you to learn, and they provide example on how to customize the codes in order to for your own needs. You also have the code that's available on their GitHub, so you can have a look. And also I wanted to mention that Parcel has been published quite a few papers for the main version that they've released. So you have quite an extensive list of publication you can go to have a look, to have more detail about the model itself, and it has been validated quite a lot. Just a few words about the installation. So they give you some good instructions on the websites, and yeah, they tell you how to install it on Linux, Windows, and macOS. You have two kind of installation: the basic or the developer installation. The developer installation allows you to directly change the code, and also I found it useful when you debug your own code. And yeah, what you need on your computer mainly is Anaconda or Miniconda. Everything is listed and well explained. So I thought before going into the codes, I would give a simple overview of how the script needs to be built in order to run a simulation with Parcel. You have 4 main components: field set, kernel, particle set, and execution on particle file that I will detail right now. So the first, the field set. So Parcels is a model that provides a framework to simulate the movement of particles within an existing flow field environment. And this velocity field can be used to advect the particle, but we can also have other kind of field like temperature that could be used to drive a state of the particle. And first we need to define, whoops, too fast. We need to define a variable or an object, a field set, using a class called field set. And here we use a method from NEMO if we want to use some output from a NEMO model, but they also provide some other method for different outputs. And this method needs to take 3 arguments. So the name of your files, the variable you're going to use to define your field set, and the dimension of these variables. So once we've done that, we have an object field set that store the field we're going to be using to move the particle in the simulation, and we're going to define. We need to define the particle in a particle set object. So these are the particles we're going to be using through the simulation. So here I define an object pset based on the class particle set provided by Parcel. And this will need to take in argument 3 main things. So first, the field set that we've just created. So we are telling that our particles are going to be moving based on this field set. We need to define the particle type. So here, GIT particle is an internal particle type that is provided by Parcel, but then you can create your own if you want to add more characteristic to your particle, like temperature, like the stage, if your particle are lavae, or you can also give an age. And the third thing is you need to provide the initial condition for the simulation of the particle. So here we give the initial release location, longitude and latitude. So now we have a second object, pset, that has all the information about our particle that we have during the simulation. And we're going to create some kernel. So this will allow interaction between the field set that we've created previously and the particle set that we've just defined. So the kernel is a little piece of code which is applied to every time step of our simulation. There are some basic kernel that are already implemented in Parcel. So, for example, here defining a kernel based on an internal kernel of Parcel, which is called advection ARK for 3D. So this is basically a kernel that will allow my particle to be advected following the Runge-Kutta scheme in a 3D dimension. So now that we have the kernel, we will be able to execute and output the simulation. So through the execution, we're going to have the kernel that will have the particle and the field set interact. And also at each time step, we will be able to save the particle location and states in so what Parcel call a particle file. So in order to do that in Parcel, there is two main functions. So first, if we want to save this particle file in an actual file, so we can analyze it later, we need to define, so here I've defined it, an object output file based on the particle file class, and then that needs to take two arguments. First, the name of the file where you're going to save the output. So here, simply called file name. But I want to draw attention on the format. This is a .zar. This is the format that Parcel is using to save the output. So you may be more used to the netcdf file format. Well, Parcel chose to change that and use a ZAR format because this is meant to be more computationally efficient. But you can easily convert it to netcdf file if you prefer. And then the second argument is the time step you're gonna save your output. And then you just have to execute with the execute method your particle set that you previously defined. And it needs to take as argument the list of kernel you're gonna apply at every time step, the runtime of the simulation, so how long the simulation will last, the time step for the simulation, and so if you want to save the results in an output file, here you provide the output file object you've created previously. So yeah, so that's the main 4 components that you need to keep in mind for a Parcel simulation. And now I wanted to show you some very simple demonstration following step by step these four components. The first one is a very simple advection diffusion test case of particle in 2D, and this is in the region of around South Africa. And the second one, if we have time, is a test where we're going to be sampling the temperature along the trajectories in an idealized test case. So I'm going to switch to Python. Okay. So the first thing you need to do, so I'm considering that you've installed Parcel, and here I am using Spider to run my Python code, but maybe you've heard about Jupyter Note, you have other options. So here, first things you need to do is to load the different model you're going to be using during your simulation. So here I load a model for handling time. This is to do plots, other things. And then here is the one we're interested in, which is loading different model to run Parcel. So you can already be familiar. You're already familiar with some of these: the field set, the particle file, particle sets. Here we have an advection kernel. And I've also downloaded some example datasets that Parcel provides. So it's going to be quicker to run the model. So first step is to create the field step. The field set here. So here we use a method from netcdf because we're going to be using some netcdf files. So now we need to define this argument, the file name, the variables, and the dimension. So you would have to define the file names for each of the variable that you're going to use to transport, to move your particle. Here we have the U and V field. they are both in the same file, so we need to give it for each of the variables. Secondly, we need to specify the U and V variables, the name that are provided in the netcdf files. So this is so we can, so Parcel can know exactly what he needs to look for into the netcdf files. So to get the U component of the velocity, Parcel will be reading the variable called Eastern Uran current velocity into the netcdf file we've provided here. And third, we need to specify the name of the variable dimension as given by the netcdf file. So here, U and V have dimension of latitude, longitude, and the time. So now we have everything to define our field set. So we can go to the second step, which was to create the particle set. So we're going to define the particles that are going to be used during our simulation. So like we saw before, we need to use a class called particle set. We define the object p set, and it takes as argument the field set. So we are telling Parcel that our particles are going to be moving through the field set. We just previously defined it. And we are giving a type for our particles. So here we're just using a simple internal class of particle already created in provided by Parcel. And we give the initial condition for particle. So the position, I'm going to create that here, longitude, latitude, and the time of release. So here we've created an array of time where we're going to have particle released every hour, and we provide that in seconds. So 3,600 seconds in an hour. And I think that's for 12 hours. Okay, so now we move to the next step, which is to create the kernel, which is going to drive the interaction between the particle on the field set. And for this example, I'm just going to create a very simple one called delete particle. So every kernel that you create needs to take 3 arguments: particle, field set, and time. So particle is saving for each of your particles the state and its location. Field set, so we've already mentioned that before, and then the time is the time we are in the simulation. And here for this kernel, all it's doing is it's saying if the particle state has any error, you need to delete my particle from the simulation. So it's not even interacting with the field set. It's a very simple kernel in order to handle any error that might be occurring during the simulation. And then now that we have set up the 3 components of the Parcel simulation, we can execute the simulation. So in this test, I'm going to be saving my output in an output file. I create that with the class particle file, and it takes as input a name. So here I call that advection test, and the output, the time step of the output. So here we're going to save the output every 3 hours during our simulation. And finally, we can execute the simulation. So again, as I explained before, we have the method execute that we apply on our particle set. This is the list of kernel that we're going to apply at every time step. So first is the advection kernel, which is going to transport our particle. through the simulation. Then we have the delete particle kernel that we just created. That's going to check for any error that are raised. We give the runtime. So here the simulation is going to last for 7 days, and we give time step, so 5 minutes. And in this case, we want to save the output in a file that we've just created here. We've created the particle file, output file. And we're just ready. We can run it. So I've already loaded some modules, so it's not happy that I'm loading them again. And here we have a loading bar. So it's showing you the advancement of the simulation. And so far, so good. And once this is finished, I'm going to be plotting the trajectories that we have created with the simulation. Okay. So Parcel provides some function to plot. So this is what I'm using. I'm not going to describe these, but you can find them on the website. So here we have the trajectory of all of particles. We were releasing them from this location, so longitude 29, latitude minus 33. And here you have the trajectory through time. So they are so close that they look just one large trajectory. And if we want to have a case a little bit more sophisticated, we can add some stochastic components to our particle. So yeah, Phil mentioned to you in his talk that usually you would have the advection components in the particle tracking model, but also you can add some diffusion on this. In this case, I'm going to do a very simple case where I'm going to add a constant diffusion to my particle motion. So here, when I was creating the field set, all I have to do is to add a constant. So it's saying that I have two constant variables, kh zonal, kh meridional, so that I'm defining. I need to use exactly those names because I have an internal kernel that is able to create the diffusion motion for my particle if I provide this constant variable. So now that I have added these constants, I can actually just add in the kernel lists one more kernel, which is called diffusion uniform kh. So I'm going to add some uniform diffusion to my trajectories. So I'm running again the model. And while before we had some very smooth trajectory, now what we're doing is, because we're going to add this stochastic component, our trajectories are going to be a little bit more random. So I'm going to be able to plot that again same way. So you can see here it's running quite quickly because I'm doing a very short run of 7 days, but you could, if you want to look at seasonality or interannual variability in particle trajectories, you would have very long simulation. Okay, so here now we have the new trajectories where you can see a lot more randomness. And on the background, you still had the previous trajectory. So we've been just adding stochastic component to the previous trajectory. And I see we're running out of time, so I'm not sure we have the time for a second one. But I can share these if you're interested. And just to finish on some notes. Yeah, again, just have a look at the tutorial and the documentation. You can have a very wide variety of test case that you can easily reuse for your own application. They have a very good community where you can ask questions about parcels in the GitHub. On the GitHub page, you just go to the discussion section. What I've showed you here is a very simple structure of how to develop your own script for particle tracking with parcel, but this can be reused for quite a few other kind of model that are usually follow the same steps, even though they can call it differently. And then I didn't go into detail at all on how to define things like the time step of your simulation. So yeah, we are preparing a publication actually with Phil to that discuss more all these different steps on how to set up your particle tracking simulation. And yeah, I will finish there. Thanks.